So now we are going to add our first unit operation, which is the valve. This is our valve over here. The inlet for this valve will be stream number 1, and this outlet will be stream number 2. So now we are going to enter the information, but here we are going at the beginning to rename this one. This is a GT valve, and GT is an abbreviation for Joule-Thomson valve. This is an expansion valve. So this valve is usually used to expand the flow and lower its temperature. So this one will be GT valve, okay? Or Joule-Thomson valve. The inlet in this case, we know that it will be stream number 1, and this outlet will be stream number 2. Even if we don't have stream number 2 out there to create it and connect it, or create it and we can connect it, because here at the outlet we don't have any option. You can, from inside the unit operation, create an external stream by writing its name. So after writing stream number 2, we have now stream number 2 created in the background, okay? So here, if we look over here, you will find out that you are asked about the delta B, or the pressure drop in your valve. Okay, so the valve has different functions. Like this one is used to lower the temperature by increasing the volume or causing expansion. Some other valves are used mainly to control the flow, or in moving forward in the dynamic simulation, you'll find out that you can create or add a valve to make a relation between the pressure and the flow. So, which is called as a flow node. So in this case, we have an inlet and outlet, and here we have a pressure drop that we are asked to add. We don't have information yet about the delta B, so which means it will be back calculated. So let's talk more about this valve. As a design connection, it's clear that we need an inlet and the outlet for this valve, and here we are dealing with only one fluid package, but be careful with the fluid package that you are choosing if you have multiple fluid packages. After that, in the design, you will find the parameter. The parameter section here is usually asking about the delta B, because the valve usually face a pressure drop, so the pressure at the outlet will be less than the pressure in the inlet. Okay, so if you have any information about the delta B, you can add it here. So this is for the user variables and notes, so we are not using this during our session. So this is, you can create your notes only. After that, we have a section for the rating. Rating or the sizing of the valve will be really crucial when we are doing a dynamic simulation, because the more accurate you simulate your valve, because valves will be everywhere during the dynamic simulation, the more accurate your results, or it will be more real. So here the rating, the sizing section, nozzles, options, and flow limits, this will be related to our section dynamic simulation. So these two, the rating or the sizing and the dynamic, will be discussed moving forward in the advanced or the dynamic simulation. For the worksheet, this is really important. The worksheet is where the data are gathered. So here we have the condition. We have already made this one as an inlet 0, and we have defined the temperature before. Here we haven't added any other information. Okay, for the properties, some of them has been calculated, because for example we have already defined propane, so we know that it's C3H8, so we have 3 times 12 plus 8, which will lead us to 44. This is the molecular weight of propane, and other properties will be also calculated. The more we added information for the conditions and the composition, the more properties will be calculated. This one is for the composition, so we can compare the two streams, the inlet and the outlet, and this is the PF spec. This is related to the dynamic simulation. Okay, so you define which will be controlled by the pressure and which will be controlled by the flow. Okay, so now we have covered our valve. The only missing information, so during the steady state for the valve, you need to define two things: the connections, which will be the inlet and the outlet, and second thing, to add the pressure drop. But we don't have information about the pressure drop, so here we are going to keep it. So after that, I'm just going to look at the our end result to know what to add next after stream number 2. After stream number 2, we are going to add this chiller. So we are having a chiller over here with a chill queue. So this one will be our first energy stream to create in this course. So back, we are going to add a heater, and okay, so now we are adding a heater, so, or a chiller, so we are looking at it like a heater. Okay, so this stream is taking energy from the surrounding, which means its temperature will be increasing, but the surrounding temperature will be decreasing. Okay, so this one we are going to double click to open it, and this one will be our chiller. So chiller, and here we are going to follow what is required. So here it required a feed stream. The feed stream, we know that it is stream number 2, and it needs also an energy stream. So not all equipment needs an energy stream. So this one needs an energy stream, so it will be Q chiller. This is the energy or the heat for the chiller. And here we have an outlet, which is stream number 3. So now we have defined our connection. We now are asked about the delta B. So here we have an inlet of stream 2, outlet stream 3, and energy stream. We are given that we have a delta B equal to 7 kilopascal, and we are also given the duty. So here for the unknown delta B, it is already given. So we can go to the parameters. After the connection, directly go to the parameter if you have more information to be added. So here we are given that the delta B, or the pressure drop, is equal to 7 kilopascal. After adding this information, we are asked about the duty. So the duty, this is the amount of kilojoule per hours, or the amount of energy that is needed to help the heater do its function. So by definition, the heat duty or the heater duty is the amount of energy. That's why this one is in kilojoule, that the heater must provide to the fluid in order to raise its temperature to a desired level. So if we look here, we have the duty and also the delta T. So you can define the delta T that you have, or you can define the duty that you have. Okay, so this is like a fast looking about some important thermodynamic concept, which is Q. So here I have added a Q chill, or our chiller. What is the equation for this one? This is the M, or the mass flow, Cp, and delta T. So if we look at our simulation, this one will be named, this is our duty. Here, this is your duty, and it will be defined in kilojoule per hour. This one is a mass, and it could be defined in kilogram per hour. This is a molar flow, so amount of mass by a unit time. So here, this one is the specific heat, and the specific heat is okay, how to describe it? This is the amount of heat required to raise the temperature of a unit mass, so by 1 degree Celsius. So the Cp will be our Q, that is for unit mass and unit delta T. So if this one is 1 kilogram, this one is 1 degree Celsius, and the amount of heat here is our specific heat. Okay, so this is specific for the unit mass. The delta T, this is the difference in temperature. So if I am increasing the temperature from 100 degrees Celsius to 150 degrees Celsius, the delta T in this case will be 50 degrees Celsius, right? This is the outlet, which is 150 minus the inlet. Okay, so this will be 50 degrees Celsius. So if we have the delta T, you can add this information. If we have the Q or the duty, we can define this information. So if we look back over here, you can define your heater or chiller by having the information about the delta T, which will make more sense and will be usually used. But in this case, we are going to define the duty. We are having information about the duty. That's why we are going to define it. So here we are given a duty equal to 1 with the power 6 So if we want to write 1 million in Aspen HYSYS, so 1 million kilo joule per hour, which is 1 times 10 with the power 6 kilojoule per hour. This time is written in Aspen HYSYS 1 E6. Okay, so this 1 with the power 6. Okay, so that's how we write 1 million in Aspen HYSYS. So back over here we have 1 E6 kilojoule per hour. So even if we have entered all the information, it is not solved because if we look back here, we have other streams that is not solved. Okay, so this one can't be solved. But let's cover the rest of information. So here, if you have information about the delta T, like we are increasing the temperature from 50 to 55, so you can add this delta T here by adding the difference in temperature, or the amount of temperature that will be increasing. If we look here at the rating section, we have information about the nozzle and the heat loss, and both of them will be covered in the dynamic simulation. So usually the rating section or the sizing section and the PF section will be covered with the dynamic. So the dynamic over here. Okay, so this is the advanced simulation. For the worksheet, it's usually what we look at when we are entering our data. So we don't have information about the stream number 2 or stream number 3, like temperature and the pressure. It is not defined yet over here. And here we have, like, if we look at the properties, some of them are calculated. The composition, both of them is 100% propane, and the PF, this one will be left to the dynamic. Here we have another section with the performance, and this will be available for compressor, pump, heat exchanger, heater, cooler, and condenser, and so on. So for the performance, here you will have information about your inlet and outlet, any plots that you want to add, and the table data will be printed in a table, and you can plot it over here. Okay, so after that, after adding our chiller, we can go over and check what information that we have. Like here we are, this is a chiller, so we are increasing the temperature of propane. So this one, over here, the worksheet, okay, stream number 3, conditions, we know that the temperature should be increasing over here. Like this one, we can add a temperature of 50. Okay, and also we know that this stream is 100% vapor. Okay, so this one will be equal to 1. So after adding these two information, we will find our simulation will be solved, like and also it will be back calculated. So here this one is not totally converged, so I want to check this one, because here I assume that the temperature will be 50. So maybe I increase this one a little bit, like 52, and okay, it's solved, but still we have a pressure on a problem over here. So if we open this one, pressure increase cross valve. So this one is a Joule-Thomson valve, which is responsible for lowering the pressure. So here it is mentioning that the pressure is increasing, and if we go to the design parameter, we have negative delta B. So with this negative means if the delta B is in the negative, which means we are increasing the pressure. So let me close this one over here and go to the chiller and enter this temperature to be like I want it to lower it like for 40. Okay, so here the temperature decreases on heating. Does this solve the problem over here? Yes. So here we need to find the optimum temperature. So if we look over here for the GT valve, we'll find out we have an inlet temperature and this is the outlet temperature, and it's totally solved. But on the other hand, we are having a temperature decreasing on heating. This will lead you to means we are having a pressure with a problem with the delta B defined. So in instead of having 7 kilopascal, I'm going to mention that I don't have any pressure drop during this performance of the heater, so it will end up having a solved heater. So if we go back over here, we'll find out that our valve is solved and also our chiller is solved. Okay, so if you have any problem with the outlet temperature, like your chiller is cooling instead of heating, this means you need to check your delta P.